Welcome back, folks, to another exciting JLAM Bio video. Today we are going to be looking exclusively at how we utilize molarity in solutions with reactions, and utilizing molarity as a way to convert between moles and liters looking at stoichiometry. So again, nothing really too terribly new, but a quick little review of how we utilize solution calculations for reactions and stoichiometry. So hopefully by the end of this video, you will be able to use balanced chemical equations and molarity to convert between species utilizing stoichiometry. And then you should also understand the basics of chemical titrations and how that impacts solution stoichiometry. So a couple different ways that we'll be looking at solution stoichiometry in this video. It's titration. Yeah. So let's talk a little bit about some solution stoichiometry. So as you know, when salts are placed in a solution, if they are soluble, they will dissociate into their individual ions. Remember that if they are insoluble, that they will not dissociate into their ions. They will stay a solid when you put them in water. This dissociation equation follows all stoichiometry rules. So if I take a look at the equation down below, we have calcium fluoride that reacts and produces calcium ion and 2 fluorine ions. So again, this dissociation equation follows the stoichiometry rules. For every 1 mole of calcium fluoride that dissociates in water, we get 1 mole of calcium and 2 moles of fluorine. This will end up being very important when we are asked to calculate the amount of ions or the concentration of ions that are in solution. But remember that ionic compounds dissociate. They break apart into their individual ions, whether it be NaCl into Na plus ions and Cl minus ions, or something like Na2SO4, which has 2 Na ions and an SO4 polyatomic ion. Please do keep in mind that when these are dissolved, they are aqueous. Remember that aqueous means dissolved in water. So for this first particular problem, we want to know what volume of 0.350 molar BaCl2 is required to obtain 0.500 moles of Cl minus ions. We're going to go ahead and ignore the second part of that question for now. We may come back to it a little bit later on. Now the question here is asking for volume. Here we're given a starting amount of 0.500 moles of Cl minus ions. Now, one thing to keep in mind when we do solution stoichiometry problems is you're going to see a lot of things with molarity. Remember that molarity is moles per liter. So that is a derived unit, and if you remember from our dimensional analysis unit, we typically don't start with derived units. So when in doubt, we're going to start with moles. So let's go ahead and start with 0.500 moles of Cl minus, because that's what's given to us in the problem. Remember that our unit on top of the first step must go on the bottom of the next. Moles of Cl minus here. Now the key here is to remember our dissociation equation for barium chloride. So if it helps, we can write that out. BaCl2 breaks down into Ba plus 2 and 2 Cl minus ions. Now that's important because in order to determine the volume of BaCl2, we need to take Cl and convert it to BaCl2. That's where we're going with this type of problem. So for every 2 moles of Cl minus, we get 1 mole of BaCl2. Okay, oops, forgot our mole. Mole or no mole. Mole. So we get moles of BaCl2. Now, the question is asking for volume, so remember whatever unit's on top of the first step must go on the bottom of the next. Now, volume is measured in liters. Fortunately, we have molarity, which is moles per liter, so we just stick liters on top. And then we utilize what we got here. So this is 3.50 moles per liter, so 0.350 moles for every 1 liter. My final unit's in volume. All of my other units cancel out. So then we just plug into our calculator and solve. So our answer utilizing correct significant figures is 0.714 liters of barium chloride. Okay. So again, it's just looking at the problem, figuring out where we're going, volume, and figuring out what chemicals we are starting off with moving forward. Let's keep going. All right, folks, we got a real barn burner on our hands here, so let's take a look at this complicated solution stoichiometry problem. When potassium iodide reacts with lead-2 nitrate, it produces solid lead-2 iodide and aqueous potassium nitrate. Write out the equation and net ionic equation. Ooh, haven't done that in a while. Hopefully you remember and can harness your inner chemistry skills. Potassium iodide, Ki, reacts with lead 2 nitrate, so that's going to be PbNO3, 2, to produce solid lead 2 iodide, so PbI2, and potassium nitrate. Need to balance our equation. All right, balanced chemical equation done. So now if we remember, we ran our net ionic equation, so we need to look at our solubility rules. Our solubility rules tell us if these are aqueous or solid when we put them into solution. And what we'll find is that Ki is aqueous, PbNO3 also aqueous, PbI2 is your solid, and KNO3 is also aqueous. So remember that our net ionic equation is formed from whatever produces the solid. So PbI2 is solid here, and that is produced from the individual ions. So Pb plus 2 AQ plus 2I minus AQ. So pretty straightforward on how to write that. Let's take a look at our solution stoichiometry problem. It says that if we started with 50 milliliters of 5.00 molar Ki and excess PbNO32, what is the maximum amount of lead iodide that can be produced? So in refer to amount, we're going to look at grams. Okay, and we're starting with 50 milliliters, and we're also given a molarity as well. So let's start with our 50 milliliters of Ki. Whatever unit is on top of the first step must go on the bottom of the next, so we'll go milliliters of Ki. The only thing we know to convert milliliters into is liters, so we'll do that. And let's keep going with our stoichiometry problem. Liters of Ki, well now I have my molarity, I can convert that to moles. Keep going. If I can write. I want lead iodide, so I'm going to go from moles of that to moles of lead iodide. And I use my coefficients of my balanced chemical equation to get that, so that's 2 and 1. And then moles to grams. Okay, so it's just following your same stoichiometry steps that you've done before. The only difference here is we're looking at utilizing tactics from solutions. We're looking at utilizing molarity as a way to be able to calculate that. And what we end up with is 5.8 grams of lead iodide. And again, very easy problem to set up. Just start with what's given to you in the problem, work your way through it, and in no time you'll have an answer. Let's move on. How would you prepare 9.70 grams of PbCl from a 0.100 molar solution of PbNO32 and a 0.200 molar solution of CaCl2? Well, the first thing we need to do is write out our balanced chemical equation for this. So let's start with our reactants. And what's nice is our equation is already balanced as we go through and do this. So in order to figure out how I'm going to prepare this, I need to take whatever material I get at the end and convert it to both of these. Basically, the question is asking for how much of one solution and how much of another solution do I have to mix to make the other. So I need to know the volumes of PbNO32 that I need to have, as well as the volume of CaCl2 that I need to have in order to make 9.70 grams of PbCl2. So let's start with the first one. Grams goes on the bottom. And we're going to go grams to moles. Again, moles of PbCl2. Go to where we want, which is moles PbNO32. 1 to 1. And then lastly, moles to liters. So 0.100 to 1. When we do that, we should get our answer. So we're going to get 0.348 liters of PbNO32. And now I just need to do the same thing for the second problem. So the setup is going to be very, very similar as the last. The only difference is we're going to just change what chemical we convert it to. Again, build it the exact same way. The only difference is now we're going to CaCl2. So my molarity is going to be different. And again, we just plug into our calculator and solve. And we end up with 0.174 liters of calcium chloride. So that's how much of each of those I would need to be able to prepare 9.70 grams of lead chloride. All right. So the last thing I want to talk a little bit about today are titrations. Now, titrations we've used in acid-base reactions before. Titrations use solution stoichiometry concepts to use a known amount of solution in concentration to determine the concentration of an unknown solution. It's really commonly used with acids and bases. If you remember, we use phenolphthalein as an indicator to determine when a reaction, when an acids and base were titrated. And remember that at the equivalence point of the amount of acid and base, it turned pink. Utilizing this information, we were able to determine the concentration of our unknown acid. Now, titrations typically use some form of indicator to determine when the amount of acid has completely neutralized, which means that it's just enough to react with the base, so our mole numbers are the same. So when phenolphthalein, for example, turns pink, we know it's reached the equivalence point. This is going to be a very powerful practice when we talk about it and go through it in a lab during our acids and bases unit. A 30 milliliter volume of aqueous sulfuric acid is titrated using 0.200 molar NaOH. The solution turns pink when all of the acid has been neutralized. The solution turns color when 48.32 milliliters of the base is added. What is the concentration of the acid? Well, before we even begin, we need to write out a balanced chemical equation for this. So let's go ahead and start with sulfuric acid. Reacting with sodium hydroxide. And that produces our salt, which is Na2SO4, and water. We need to go back and balance our equation. Okay, now we're in good shape here. The question is asking for the concentration of the acid. Remember that concentration is molarity, which is moles per liter. Now what's nice is I'm given the volume of the acid itself, 30 milliliters. So that's going to end up going on the bottom here. But I need to know the number of moles of acid that reacted. Well, in order to do that, I'm going to have to start with my base. I know how much base I added, so let's go ahead and start with that. 48.32 milliliters of NaOH. Milliliters to liters, the only thing we can do with it. I know my concentration of my base, 0.200 moles per liter. So for every 1 liter, 0.200 moles of my base. The last step here is utilizing the equation. We're going to go from moles of base to moles of acid, because that's the part that I'm missing up at the top here. I need moles of acid. So that is a 2-to-1 ratio. So let's go ahead and calculate that. So what I get for moles is 0.0. What I get for moles is 0.00483. And since that is my mole number, I have liters, 30 milliliters to liters, 0.030. All right, and then I just divide the two, and that'll give me my concentration. Using correct significant figures here, we're going to end up with 0.161 molarity, big M, H2SO4. Okay. So again, just a couple different ways to look at utilizing molarity as a way to be able to go through and complete some stoichiometry problems. Hopefully pretty straightforward for you guys. Let's move on. So as I mentioned before, hopefully you're able to use balanced chemical equations and molarity to convert between species using stoichiometry and understand the basics of titration. Titration works very similar to a stoichiometry problem. We just need to figure out what we need and where we're going to get there, utilizing the molarities, of course. Hope you have a great day, guys. We got one more video of this unit, and then we move on to the new stuff. We will talk to you later. Bye-bye.